continue our journey through alkanes and other hydrocarbons. So since the difference in electronegativity between carbons and hydrogens is minimal, it's less than 0.4, alkanes are nonpolar, unless they have a lot of substituents in a certain way. Then it's a different story. They are insoluble in water, yes. They usually less dense than water, especially the ones that we use, flammable, and we extract them from natural gas or crude oil. Okay? So, the oil spills, what the problem with them? Well, there are two problems. Less dense than water and insoluble in water. Since they are less dense, they form the film on the surface of water that restricts the access for oxygen. And number two, if they cover any living creature, they can't be washed off because they are insoluble in water. And that is, dying birds. I'm not even talking about potential toxicity, but that's what those oil spills do. Just as an example, by the way, we happened to live in Louisiana when Deepwater Horizon exploded. Remember I just realized many of you were, it reminds me about my age, but yeah. So in 2010, oh shit, yeah, you don't remember. Huh? 2010, 2009, there was a oil rig in the Gulf of Mexico that exploded, and enormous amount of oil got out, and we went to the Gulf Coast 1 year after they sealed it, and we were like, the Gulf was fine, but we were finding clumps of oil on the beach, black tar clumps. So, since bonds between carbon in alkanes are very strong, they can burn, releasing a lot of energy, producing carbon dioxide and water. Okay? So this is the reaction for methane to burn. Now, natural gas that we burn in our stoves is mostly methane, but it also contains a fair amount of other gases like ethane and propane, just in a smaller percentage. Now, the gas that you buy to use in things like gas grills, it's a propane. It's not methane. Now, butane is the gas that is used in those small portable burners. The reason is because it contains 4 carbons. And therefore, when you burn a certain amount of, it releases a lot more energy than, say, methane. So this is why it is more expensive. So propane, which is used for not barbecuing, but grilling, will burn producing water and carbon dioxide. If you want to tell me the coefficients to make this reaction balanced, right away, go for it. Otherwise, we can have fun balancing it. Any? Okay, what? Okay. 3? Wait, it goes wild now. 4 in front, okay. Five. I think we're good. That's it. Okay, and obviously a lot of energy. Okay? Yeah, you're absolutely correct. Now, some compounds, carbons can form more than one bond between themselves, forming a triple bond or a double bond. The bond is double. We're talking about alkenes. If the bond is triple, we're talking about alkynes. Okay? We call them unsaturated because they don't have all possible hydrogens. They're not saturated by hydrogens. And therefore, they contain double bonds. They can react with hydrogen to replace a double bond with 2 hydrogen bonds. Replace one bond in a double by 2 hydrogens. That's what I was going to say. So alkenes, this is the simplest one because unless you have a bond, you cannot be an alkene. It is ethene. So you see the difference between this compound ethane and this compound ethene. It's the ending. Now we are going to play with the ball and stick models, and if you try to think how this is organized, these 2 carbons have to be located on the same line in the same plane. Does that make sense? Right? You cannot rotate them. There is no rotation around that bond. Does that make sense to you or not? Like if you connect 2 wheels with one axle, wheels can, circulate, rotate around that axle. But if for some reason you connect 2 wheels with 2 axles, that's where rotation stops of each individual wheel around any of the axles. Okay? So this molecule is in a single plane, and all the angles between the bonds are 120 degrees. The common name for ethene is ethylene. And ethylene is surprisingly one of the plant hormones, that is true, that facilitates ripening of the fruits. And there are actually certain combinations. Well, first of all, here's a good example, bananas. These are bananas. What color are they? Green. Why are they collected green? Well, yes, but why don't we collect yellow bananas? Say again? Right. On the way to the grocery store, they will go bad. So they would collect green bananas, ship them, they're pretty resilient, blah, blah, blah. Then before getting them on the shelves, they will treat them with ethylene. They will ripen really fast. And now you have proper bananas. Okay? Alkynes. So in alkynes, 2 carbons are connected by a triple bond, and each of them is connected to another hydrogen, which means the bond angles are all going to be 180 degrees. Because, you know, this is the optimum. They are all arranged in a straight line. Okay? So ethine, also known as acetylene, if anyone is into welding, one of the gases that is used in some types of welding, okay, or cotton metals. So far, so good. Now, the presence of a double bond specifically explains the existence of another type of isomers called cis-trans. So this illustrates pretty well the whole cis-trans idea. So cis means on the same side, trans means on the opposite side. Does that make sense? Is it making sense to you? It's been a long week. So we talked about the idea that if you connect two carbons with a double bond, this connection becomes rigid, and there is no rotation. In other words, as we say, if you have two carbons connected by a double bond, the only way to rotate is to break one of them, which isn't going to happen. It means that the groups that are attached to these two carbons, they will be holding their positions, there will be no rotation, and once you attach those groups, they're not going to change their orientation relatively to each other. So, for instance, here is a great example of dichloroethene. This bond essentially represents sort of a borderline, or the central axis of the molecule. In this molecule on the left, two chlorines are on the same side. Can you see that? The molecule on the right, they are on the opposite side. So in addition to the name that shows where substituents are, 1,2-dichloroethene, in many cases, in the molecules like this, you have to specify the arrangement of the substituents relatively to the double bond. So why this is important? The arrangement dictates the chemical properties, and indeed cis and trans isomers have different properties. One of the example that you can see in the real life. Do you use cooking oil? Yes. Right? I hope the answer will be no, but do you use vegetable shortening, like Crisco? Good. But it exists, you know it. Well, vegetable oil, cooking oil, is liquid. Am I right? What about things like Crisco or margarine? How do they look? Solid. You know, they contain cis and trans isomers of pretty much the same molecules of fatty acids. But trans isomers are solid and cis isomers are liquid. Okay? So this is another example of cis-trans isomer. This is the molecule that contains 4 carbons, right? Good? We're going to learn the nomenclature as we go along. 4 carbons. What is the prefix for 4? Bute. Bute. I told you, first 4 make no sense. Like meth, eth, prop, and bute, no sense. So, bute. Molecule contains double bond. Right? So it's got to be ene. So butene. Now, butene. Do we need to show where this double bond is? What is its position? We do, because it can be here or in the middle. So we give it number 2. Remember, the lowest number possible. So it shows you that double bond is at the second carbon. And then we'll look at substituents. So each carbon here is connected to one hydrogen and one other carbon. One hydrogen and one other carbon. All right, sounds good? Okay, so there can be a position when these two carbons are on one side of the double bond or when they are on the opposite side. Cis, trans. Okay? Now, pheromones, the chemicals that insects produce to communicate with other insects, are essentially organic compounds. Okay? And the effectiveness of these pheromones is basically determined by having a trans or cis conformation. So which on this image, which conformation is cis and which is trans? Say again? Yes. Because same side, opposite sides. So in this case, since we are talking about an alkene that contains only 2 carbons, can you see that? 2 carbons. We don't have to number where the double bond is. There are no alternatives. 2 bromine substituents, opposite ends, so 1, 2, dibromoethene, and then based on the line angle formula, we add cis. Okay? Or trans, depending. So what I'm trying to tell you, by the way, if I would tell you, please draw me 1, 2 dibromoethene, your first question should be, well, do you want a cis isomer or trans isomer? Because they're different. Right? Make sense, everybody? So let's see if you can name the following molecules. What would you call this one? How many carbons? Let's do it methodically. How many carbons? The prefix but, in, because there's double bond. Okay? What is the position? Do we need to put the number for the double bond position? Yes. What is the number? 2. And then substituents? Just 1 chloro, or so dichloro, not 1, 2, because if it's 2, it's got to be 3, 2, 3, and cis or trans? Cis. Make sense? Good? Can we skip all those boring steps and you just tell me the name of that B compound? Go on. You tell me. I'm not telling you. Wait. 2, 3. Just bromo? Dibromo. 2 butene. Do you need to add cis or trans? Yes. What should be? Trans. And the bottom one? This is the easiest, the softest ball that can. You basically have to take other answers and just throw some stuff out. Also trans. What is the longest chain? So that's it. It's 2-butene, right? Does that make sense? 4 carbons, E and E. There are no substituents. All you need to do is to show where double bond is. Okay? So, this is what I was talking about. So we've got some fats. Good.
Before we move on, the solution 1, why isn't it saying like 2-butene like we've been saying in that answer?
They wrong?
They're wrong?
Yeah. It should be. Because what if we put double bond here?
Yeah.
Like modifying stuff and, but yeah, it is not correct. There should be a number for a double bond. So, we're going to talk about fatty acids. We're going to talk about fatty acids later as well. But so this is oleic acid. It has double bond, and it is found in large proportion the oils. Okay. This is stearic acid at the same spot. It has a single bond. So this one comes, for the most part, from things like, literally fat, like animal fat, like pork fat. When you add hydrogen, almost literally bubble hydrogen, through vegetable oil or canola oil or whatever cheap oil that you can get from plants, like corn oil, you saturate the double bond and form a single bond instead. So you're turning liquid, cheap plant fats into solid fats. Right? Does that make sense? Good? It all sounds great. There's one little problem, that some cis unsaturated fats, they become trans unsaturated fats, and trans unsaturated fats are very bad for your cardiovascular system. So don't use vegetable shortening or Crisco. Okay. So we've covered so far alkanes, cycloalkanes, alkenes, and alkynes. Brief question. What do you think? Are there cycloalkenes? Yes. Cycloalkynes. Sure, why not? You can introduce a triple bond in a cycle. It's going to be a very weird cycle, hard to synthesize, but you can do that. Like you can produce triple bond, okay, something like that, and then, well, actually 2. 4 bonds. So it can be done. It's not easy. Are there molecules with more than one double bond? Sure. Double and triple bond. Yes. The reason why we don't talk about them, we just want to illustrate all, different possibilities for organic compounds to organize themselves. Aromatic compounds are different. So they are called aromatic, not because they smell good, but because they smell strong. Okay? And for the most part, it's not great. So the simplest aromatic compound is benzene. Okay? So 6 carbon atoms, okay, and 3 double bonds. That makes sense? Now, if you look at this illustration, this molecule and this molecule have different arrangement of double bonds. Can you see that? So these structures, when the arrangement of the bonds is different, but like slightly different, but functionally they're the same, you can easily see how these bonds will be changing within the molecule without breaking down the molecule fundamentally, okay? These are called resonance structures. And what it means is that at any given time, we assume that half of the molecules in the sample are in the left state and half of the molecules are in the right state. Now, partially to reflect this, we draw, instead of figuring out which double bonds to form, we represent it with a circle. And we can remove all the hydrogens, and this is the common symbol for line angle formula for benzene. Okay? But it's not the only reason why we do that. It's not the only reason why we draw the circle. We're going to get to aromatic compounds. Which particles found in an atom form covalent bonds? Electrons. So here you have 3 double bonds, 3 bonds that are very rich in electrons, located adjacent to each other. So it means that electrons, rather than bonds, let's say this way, bonds, rather than belong to a couple of carbons, become, it's like basically benzene is a communist molecule. All carbons own all electrons. Okay? It is equally shared. Now, aromatic compounds actually provide a pretty rich selection for like naturally occurring things. So this is the formula for vanillin. Aspirin, which was it was a modified version of a drug isolated from the bark of some tree, aromatic compound. Acetaminophen, you know it under the brand name Tylenol. And this is TNT, trinitrotoluene. There are different relatives of that compound. They all are explosive, but TNT is the best. Okay?